Hello, 2nd of April. Let's see if we can finish problem 2 today. N is odd, then Tn commutes with alpha 4. That was part A of problem 2. It preserves each eigenspace. Does it now? What I recall about commuting operators was that the matrices could be simultaneously diagonalized. But that was operator theory, so let's just look at it. So assuming AB commutes and V is an eigenvector of A, since B is linear. Oh, so that means that if lambda is non-zero, then BV is an eigenvector of A. That's what they mean, that B conserves the eigenspaces of A. All right. So that's the eigenspace of alpha 4 they talk about. I actually wrote up as preparation the eigenspaces for alpha 4 and for T2. Oh yes, because Tn also maps this eigenspace into itself. So let's take alpha 4 of F is an eigenvector of Tn. Of course, n being odd. But alpha 4 of n equals, now what was that? Minus 1/16 theta to the 4th plus F. I think that was what we had. Yeah. But T to 4 this guy is eigenvector of Tn 2. So we have two eigenvectors of Tn. What was alpha 4 of theta? You see, I would actually like Oh, it has the same eigenvalue. So this one has eigenvalue, f had eigenvalue naught. Because f has eigenvalue naught. That was modulo T2, so we don't know what the eigenvalue. Now, confusing again. That was an eigenvalue of T. Yeah, f is an eigenvalue of T2. That means T2f is an eigenvalue of Tn, but that's naught, so that gives us nothing. So we must do it on these eigenfunctions. Alpha 4 so that means theta to the fourth is eigenvector of Tn, and alpha 4 of f minus this feels wrong. If we have an eigenvector with b, with a, then b of it. So I'm using the same twice. So we should apply Tn to these guys, then we'll get another eigenvector of alpha 4. So you see, we get Tn of all of these guys are eigenvectors. And could it have the eigenvalue naught, any of them? I really think it can't. Because now if we take Bm, Tm, and then take the first coefficient, I believe that's, that's actually in the book. it's a mn, and that was a m. So we can just write n instead of it. I think I'll do that. And since n is odd, they are all non-zero, so it doesn't map onto naught. So Tn of theta 4 and Tn of f and all linear combinations of them map into eigenvectors of what? Of alpha 4 and T2. What should we show? Oh yeah, it's Tn so I don't this way get an eigenvector of b. And that was the point, that we should show that they were all eigenvectors of Tn. And we know that they are eigenvectors of alpha and T2, respectively. We could use the end of the section where they show that they will have eigenvectors, and then make a linear combination of those, and then apply alpha 4 and T2, ZZ with T2, then F is mapped to north, so only the component of theta becomes an eigenvector. Well, then we are home, basically. So I'll check if we can be sure that Tn can be diagonalized. So I'll just check that. Right, it turned out to be the last proposition of the section, proposition 51. Assuming minuscule and capital N are coprime, the space of cusp forms is spanned by eigenforms of Tn. In our case, the cusp space is generated by capital F. So that means that F are eigenforms of Tn. All right. And that means alpha 4 of F is as well. And then it's trivial that theta to the fourth is as well. Simply by subtracting the two. and with the same eigenvalue, mind you. So that means that all of M2 of gamma 4 is the eigenspace with the same eigenvalue. So we just need to find it, but now we can use proposition 40. It fails for cusp forms, but it holds for theta to the fourth. And if it's normalized, and that was 1/16 theta to the fourth, as coefficients a n equals but n is odd, so all the divisors are odd. So chi of d is unity, only vanishes for even numbers, and that's just the sum of divisors of n. My God, that was what we should prove. And finally, we need to, was that E or D? That was E. So this is actually part D I've been working on. The coefficients of, we have 1/16, or was it 1/8? I was 1/8. Theta to the fourth is the sum theta 1 of n. So it's 1/8 plus sigma 1 of n q to the nth. And that means that the now what do they call it in the problem? Oh, an, yeah, the sum of, so poor notation. So if we call this Cn instead of, then we get the an of the problem being 8 times this that was the first half. The next one is to find out what happens when n is even. I have absolutely no idea. Nope. We'll leave that for the moment. I'm back immediately. I have to go shopping. I need to buy some new furniture and a jacket for the spring here. The other one's got a hole in it. But while I was drinking my coffee, I got an idea. And that's to, if we have n equals 2 to the rth n naught, where n naught is odd, then we can use the operator t 2 to rth, because there we have b n equals b n times 2 to the rth, particularly a should be a, of course. Particularly b1 is a2 to the rth. And T2 and Tn commute. So this should be an eigen. So T2r of this function should be an eigenfunction, an eigenvector of T2 as well. With the same eigenvalue, which means it should be proportional to this guy itself. I'll just have to look at it another time. So today's Wednesday. I don't know why I wasn't able to finish it yesterday, but I believe it was an old confusion whether or not t to rth was the same as t2 to rth. I remembered a complicated formula from the book, but that holds when 2 fails to divide n, and this is the case where it does, so this does hold. And that means that this is, that should be n naught. This is the coefficient we want, and when we operate with tr, then we should operate on this guy, which has eigenvalue 1, and the even coefficient here has no contribution from f, which means that's exactly 1/24th of the guy we're interested in, and we already know that's equal to sigma 1 of n. So that means we get, the coefficient here, that's 1/24th of the sum. So we get the sum equals, what do we do here? The sum of divisors equal 24 sigma 1 of n naught, which was what we should prove. When I majored in math, I took a course in classic number theory, and this was actually a theorem we proved in that course. I only have a very vague recollection that we had to use a lot of tricks to get through it. Of course, we do that with this proof as well, but it was very satisfying to be able to prove it again.